Here. Okay, perfect. There's another question. Okay. All right. So yeah. So let me first start with the integral, the single variable. So I'm gonna just remind you, the basic definition of integral of single variable, and then of course, I will move to the double and triple integral. Right. So let me first recall you some basic definitions. So this is, I would say, it's from Calc 1, Calc 3. So I'm going to start with a single variable. Okay. So we start with, of course, some function f as a single variable, x. Okay. Of course, we need f to be actually a continuous function. So f of x be a continuous function. Okay, on some interval AB. Okay. And for the moment, let's suppose that this function f is positive, but it's not, of course, it's not a requirement, but we'll see what happens when the function f is not necessarily positive. So let's say let f of x be a positive. Right. So you have this interval AB. Here's my A. So this is your number line. So you have your A, you have your B, and you have your function f, a continuous function f over this interval AB. And we suppose that this f of x is positive. So let's say here's my f of x. So this is my function f of x on the interval AB. Right. And now let's say we have you want to compute the area bounded by the function f and the x-axis. So here's your x-axis. This is your y-axis, of course. And so we have this region, this one here. So this region S, this blue region S. All right. And so the goal here is, of course, to compute the area of the region S. So S so S. So this is the area bounded by by the function f of x and the x-axis. Right. And of course, as I said, the goal is you want to find the area of S. Okay. So the idea, so just to remind you again, the idea here would be to first to divide the interval AB into subintervals of equal width, right? So the first step would be to, so step one, so we're going to divide, so this interval AB into n subintervals. Okay, of equal width. And I'm going to denote the width by delta x. So the width delta x. What will be the width delta x? So I have this interval AB, right? So what's the length of the interval AB? So what's the distance between A and B? Well, if you have an interval AB, yeah, it's B minus A. Thank you, Dylan. Yeah, absolutely. So it's B minus A. And so that's the length of my interval. And I'm going to divide it into n subintervals. So I'm going to divide this distance, B minus A, over n, right? So what I'm saying, guys, is that I have this. So here's my interval. This is A. Here's B, right? So I'm going to divide it into n subintervals. So let's say this is first subinterval, second subinterval, third subinterval, etc., and then the nth subinterval, right? So let's call, so A0, I'm going to call A0, sorry, I'm going to call A x0. So this A here, I'm going to call it x0. The next point, I'm going to call x1. Next point is x2, x3, etc. And B would be my x subscript n. Okay. As I said, so I'm going to call the endpoints of the subintervals x0, x1, etc., xn. So we have n subintervals. So we have the first subinterval would be x0, x1. Next subinterval is x1, x2, then x2, x3, etc. And then the last subinterval would be from, so just before x subscript n, we have, of course, x subscript n minus 1, right? And then x subscript n. Okay. All right. So again, the x subscript 0, 1, 2, 3, etc. They are just the endpoints of my subinterval, right? So the x subscript I, this is just the endpoints of my subintervals. Now I have my function f. So here is my function f. Let's say here's my function f of x. All right. And now because I have n subintervals, so we're gonna have n, let's say, subregions. Or so first subregion would be this one here. Let's call it S1. So this one here, this is S1. All right. Now the subregion corresponding to the subinterval x1, x2 would be, let's call it S2. So this is here S3. All right. And the last subregion would be Sn. This one here, Sn. Right. So what we did here, guys, is we divided our area S into n sub regions, right? S1, S2, S3, etc. Right. Now, so I want to approximate. So we have n subregions. Right. So S1, S2, etc. Sn. Right. So I'm gonna approximate the area of the area SI with a rectangle. The area of SI, the subregions. So subregion SI with a rectangle. Okay, of with delta x. So as I said, guys, here, so I divide my interval into n subintervals. So here, this is this width here. This is the length of this subinterval is delta x. The length of this subinterval, of course, is also delta x. This is also delta x, etc. Right? Because all my subintervals are of equal width, right? Delta x. And so now I want to approximate this subregions. So what I'm going to do, I'm going to multiply my with delta x with f of xi, let's say. So for example, here this is x1, right? So here this is f of x1. Here this is f of x2. F of x3, etc. And here this is f of b or f of xn. All right. And so when you multiply delta x, for example, with f of x1, we're going to have the area of this rectangle here, right? This one here. Right. Delta x times f of x2, for example, would be the area of this rectangle, etc. Right here. Delta x times f of x1 would be the area of this rectangle, right? Now, these rectangles, they approximate our, our subregions, the area of our subregions SI, right? So our area S, so conclusion here, so conclusion is that our area S, which is the sum of the area of S1, area of S1 plus the area of S2, right? Plus the area of S3, etc. The subregion S3, etc. Plus the area of the subregion Sn, right? Now I'm going to use summation notation. So sigma. So this is sigma. This is our sum. Okay, so this is the sum of the area of S subscript I, and I, of course, I goes from 1 to n, right? Because we have S1, S2 to Sn, right? So the subscript I goes from 1 to n, right? Now, as I said, each subregion SI is approximated with the area of the rectangle, let's say delta x times, f of xi, right? So I can approximate this, my subregion. So this is approximately, right? The sum going from 1 to n, f of xi times delta x, right? So again, guys, this f of xi times delta x is just the area of our rectangle. This is the area of rectangle. okay, which approximate the area of SI, right? Um, so actually this sum here, sum of f of xi times delta x is called the Riemann sum, right? This is called the Riemann sum. So Riemann, of course, is he's a German mathematician, right, from the 19th century, right? It's very well known German mathematician, right? So Riemann sum, right? Now the idea, of course, again, the goal is to, we want to compute the area of this region S. Now what we can do is we can increase the number of sub intervals. As n gets large, right, we're going to have a better approximation of the area of S, right? So we increase the number of sub intervals as n gets large, and we're going to have a better approximation. And so as n gets large, okay, so what does it mean for n to get large? It means that we're going to increase the number, we increase the number of subintervals. Right? So your subinterval is going to be very, very small, right? You're going to have a very, very small subintervals. And then, so your rectangle would be the area of your rectangle would be very, very close to the area of your subregion SI, right? So here you can imagine, for example, this is your rectangle and this is your, this is your subregion SI, right? So yeah, so you're gonna have a better approximation, and so actually the area of S would be the limit. So the area of S is gonna be the limit n approaching infinity, so n going to infinity of this Riemann sum. So I going from 1 to n of f of xi delta x. Okay, and so this is by definition the integral of f of x over the interval ab dx. Okay. So let me just here, guys, emphasize on the fact that there's I think there's a comment in the chat. Yeah. Let me just say, guys, here that this dx or delta x represents the rate of change of the length, and actually, so this delta x or dx. So this delta x or dx represent this represents, the rate of change of the length. Rate of change of the length of your, length of your subintervals, right? And I will call this dx or delta x the length element. Okay, so I'm gonna call the length element. Right? Why it's called the length element? Well, in some sense because it allows you to compute the length of your interval AB, right? So because if you just integrate dx. So let me just make a couple of remarks here. So yeah, so this dx is called length element because allows you to compute the length of the interval AB. Right, because if you do just the integral, if you do just the integral of let's say 1 dx over the interval AB, this is just the integral of 1, of course, is just x, so that would be x from A to B, and x from A to B would be B minus A. All right, and so that's exactly the length of our interval. So this is actually the length of the interval AB, right? So that's why we call this dx length element, right? I mean, we're gonna see later in the next sections, like if you have, if you have like a surface or a volume, then we'd have, area element or a volume element, etc. Right? Anyway, so this is the first remark. Second remark is that, as I said, if your function, of course, is not positive, if f of x is not positive, your integral actually is going to give you the net area, which means, so if f of x is not positive, right? If this is not positive, it's not a big problem, because and this integral would be dx gives you the net area, which means, so if you have a region, the net area, right? So which means the following. So if you have, let's say, some function f, which is not positive, for example, say here, all right, and you have this interval AB, all right, and you have your function f. Let's say here's your function f of x, right? This is your f of x. All right, so then the region bounded by your x-axis, and so the region S bounded by the x-axis and your function f would be this one here, right? So obviously this function f is not positive, right? So you have this this region here is under the x-axis, right? So because it's under the x-axis, your function f is negative, right? So the area of this region comes with a negative sign, right? So this gives comes with a negative sign. And this one, of course, because it's above the x-axis, it comes with positive sign. Right? So when you integrate your function f in this case, then what you get is basically the difference between these two areas, right? The one above the x-axis and the one below the x-axis, right? That's what I mean by the net area. Anyway, so I guess, so this is from, this is just a, the single variable. I mean, I guess you did this in Calc 1 and probably in Calc 3 too. But let me give you a couple of examples because we're gonna need this Riemann sum later in the next sections. So I'm gonna do a couple of examples to show you, that this Riemann sum really works, and so let's do a couple of examples. Example. Okay, so let's say you have the function f of x equal to x. All right, and let's say you have interval, AB equal to the interval 1, 2. Right? So, you know, so you have this is 1, this is 2, and you have your function. Let's say this is 1, here's 2. So you have your function f of x over the interval 1, 2. F of x is equal to x, right? So this is your function f of x, and so the region S would be this one here. This would be your region S, right? This one here, right? And so you want to, let's say you want to compute this, the area of the region S using the Riemann sum first. Okay, so I'm going to use the Riemann sum first, and then we will do just the usual integral, right? So if you want to use the Riemann sum, so how does the Riemann sum work? Well, let me just remind you that definition. So we said, so this area of S, the area of S would be equal to, so the area of S, right, we said would be equal to the limit and going to infinity, right, sum, over, so I going from 1 to n of f of xi delta x. Okay, again, delta x is your length element. So that's the Riemann sum, right? And so what would be the formula for delta x? So delta x, we said it's just you know, b minus a over n, right? So b, of course, would be you know, b is 2 and a is 1, so that's 2 minus 1 over n. So that's equal to 1 over n. That's delta x, right? Okay, we got our delta x. Now what about f of xi? So first, what's xi? Well, so xi. So remember, guys, for xi, you know, so you have your interval ab, right? So this is supposed to be x0, x1, x2, etc. And this is little b would be xn, right? Subscript n. Now, so we said, so the width here, this is my length element, delta x, this is my delta x, etc. Right? So for example, x1, so for example, x1 would be equal to, you know, x0 plus delta x, right? I mean, the distance between x1 and x0 is the delta x. So then x1 would be just x0 plus delta x, right? All right, because it's distance between x1 and x0 is delta x. Now, if you want to, x0, of course, is just a, right? So this is just a plus delta x. Now, if you want to compute x2, x subscript 2. Well, x subscript 2, the distance between x subscript 2 and x0, it's twice delta x, right? It's 2 times delta x, right? So x2, x subscript 2, it's x0 plus 2 times delta x, right? So etc. So in general, if you have x subscript I, so then x subscript I would be x0 plus, well, I times delta x, right? So this xi is just x0, and again x0 it's a, right? So it's just a plus I delta x. So this x subscript I, it's a plus I delta x, right? So my xi is just a. We know a is 1 in our example, plus I, and then delta x is just 1 over n. So it's I times 1 over n. Okay, so my xi is just 1 plus I over n. Right, so I got, so that's the formula for xi. It's just 1 plus I over n. Okay. Now, so again, guys, I wanna apply this Riemann sum, right? I got my delta x, it's just 1 over n. Now I want to compute f of xi. We said xi is 1 plus I over n. And so now what will be f of xi? Again, guys, please feel free if you have any question, feel free to interrupt me, right? Or you can write down your question in the chat. Anyway, so f of xi, f of x, our example, we said in our example, f of x is just x, right? So f of x is x. So if you want to compute f of xy, right, you just replace x by xi. So it's just xi, right? And xi, we said it's 1 plus I over n. Right, so we got our f of xi. Okay. Now, so now let's apply this Riemann sum. So now we can compute the area of S. Which is, we said, limit n going to infinity of f of xi times delta x. All right. Now, sorry, sum here, of course, for the summation here, right? I going from 1 to n. All right. So, so I know I know f of xi. It's just 1 plus I over n. So this would be equal to limit n going to infinity, sum I going from 1 to n. So f of xi, well, here's my f of xi, it's just 1 plus I over n. So this is just 1 plus I over n times, and then delta x. Delta x, we said in our example, delta x is 1 over n, right? So it's just times 1 over n. Okay, so in other words, this is a limit n going to infinity, sum I going from 1 to n. So 1 times 1 over n is just 1 over n, of course, plus, and then, so I just distribute, guys, here. So I times 1, it's I over, of course, n squared. All right. So let's just split this sum here. So we have a limit n going to infinity. So first we have the sum of 1 over n. So sum I going from 1 to n, 1 over n. Right. And then plus, and then they have this sum of I over n squared. I over n squared. Right. So again, limit and going to infinity. So I have to compute this sum here. So first I have this summation here, I going from 1 to n. So when I is 1, I see there's a question, Dylan. Sum of series. Yeah, I mean, that's what I'm actually kind of I'm doing here, right? So this Riemann sum, right? You know, it's a series. So in some sense, that's what I'm doing right now. Yeah, absolutely, Dylan. So this is, yeah, so this 1 over n. So you have when I is 1, you have 1 over n. When I is 2, it's 1 over n. When I is 3, it's also 1 over n. All right. There's no I here, right? So for any I, we're gonna have just 1 over n, right? So etc. plus 1 over n. So how many times Well, we're going to have n times, right? Because I goes from 1 to n. So here, this is n times. All right. Now, the second sum, it's here, I over n squared. So we're going to have a plus. Right. So when I is equal to 1, so if you replace I by 1, we're going to have 1 over n squared. So we're going to have plus here, 1 over n squared. When I is 2, we're going to have 2 over n squared. When I is 3, we're going to have, you replace I by 3, right? So we're going to have 3 over n squared, etc. And of course, when I is equal to n, so we're going to have n over n squared. All right. Anyway, so this is equal to, so first we have this sum of 1 over n, n times. So it's just, again, you have a limit, of course. Don't forget the limit. So we have n times 1 over n. So it's n times 1 over n plus. Now, for the second sum, this one here, right, you can see there is a, a common factor, which is n squared. You can, you can factor out the n squared. There is an n squared. So it's 1 over n squared times, that's our common factor, right? N squared, the denominator. And then in the top, we're going to have, 1, and then plus 2, plus 3, plus etc. plus n, right? Yeah, so now the question, guys, what will be, so we need to find the formula for 1 plus 2 plus 3 plus etc. n. So what will be, do you know any formula for this? The sum of 1 plus 2 plus 3 plus etc. plus n?
N times n plus 1 over 2.
Yeah, absolutely. Very good. Thank you. So that would be, limit n going to infinity. So this n times 1 over n, it just, of course, will be n over n plus 1 over n squared. And then this sum here, 1 plus 2 plus 3 plus etc. n, that will be n times n plus 1 over 2. Okay. So this is actually this formula, I mean, for this, this formula n times n plus 1 over 2, it's actually kind of a nice, I mean, it's easy to see. It's not a big deal. If you want me to prove this formula, I can, of course, I can show you how we get such formula, right? But anyway, so this would be equal to limit n goes to infinity, so n over n is 1 plus, and then you have this n times n plus 1 over 2n squared. Now we need to compute the limit, right? So what will be the limit of this term here, this one here? So n is going to infinity, right? So when n or x or whatever goes to infinity, and you have a polynomial, in the top and a polynomial in the denominator, right? So you have to compare the degrees, right? So the degree of the top here, it's 2 because we have n squared, right? So this is mainly n squared, all right? And here it's 2n squared. Right, so it's n squared over 2n squared. So it's just so the limit actually would be just half, right? Right, because again, guys, anyway, if you have a question about the limits, how we compute the limits, just let me know, right? But I assume that you know how to compute the limits. But anyway, so in this case, in the top, the highest power of n is 2. In the bottom, the highest power of n is 2, right? So when you have the same power in the top and in the bottom, all you have to do is to take the ratio of the leading coefficient. So here we have 1 n squared, and here in the denominator we have 2n squared, right? So the limit n goes to infinity, the limit would be the ratio, it's 1/2, so it's half, right? So so the limit here would be equal to half. So anyway, so the answer would be 1 plus 1/2, and that will be, of course, 3/2. All right. So when you use this Riemann sum, you get so the area of your region S, and it's actually just 3/2. Now, if you do just the usual integral, if you integrate, so our example is f of x is equal to x, right? So if you just integrate x, the function f of x, which is equal to x, over the interval 1, 2, you're gonna have so if we integrate now, okay, so now if we integrate, so the area of our region S would be the integral of f of x, right? Length element dx over the interval 1, 2. So it's from 1 to 2. So it's just the integral of x. That's my function f dx 1, 2. Integral of x, of course, x power 1. It's x squared over 2. It's x squared over 2 from 1 to 2. So if you replace x by 2, you get 2 squared over 2 minus, and if you substitute x by 1, you get 1 squared over 2. So it's minus 1/2, right? So it's 4/2, which is 2 minus 1/2. 2 minus 1/2, of course, common denominator, that will be equal to 3/2. And of course, you're going to get the same answer. So anyway, guys, so just so this is just to remind you how definition of integral using the Riemann sum, and of course, what you get is the area of this region S. Right. So that's for a single variable. Is there any question first, guys, about this single variable case? All right, so now let's just move to the double integrals, right? So now we're gonna have functions of 2 variables. So now let's move to the double integrals. So the idea is, again, the same. We're gonna try to approximate. So single variable, the goal was to find the area of some region. For double integral, the goal would be to find the volume of some solid, right? Anyway, so we start with the function of 2 variables, f of x, y, right? Of course, we suppose that this function f of x, y is a continuous function, is continuous on the rectangle let's say AB times CD. So when I say the rectangle AB times CD, so here we have 2 variables, right? Now we have 2 variables. We have x, we have y. So we have this is my, let's say, x axis, this is my y axis. And now I have, so first I have the interval AB. So AB, this is the x axis, and this interval CD, it's on the y axis, right? So on the y axis, we have the interval CD. Okay. So now when I say AB times CD, that will be this rectangle here, this one here. So this is So that's what I mean by AB cross times CD. So this rectangle here. Okay. So this is my rectangle AB cross CD. So again, AB cross CD means that my X belongs to the interval AB and my Y coordinate belongs to the interval CD, right? Now, I have this function f of two variables, right? So I'm gonna need, so if you wanna graph this function of two variables, of course, you're gonna need a third axis. Now, so we're gonna need a third axis. So here's my x-axis. So let's say this is my x-axis, this is my y-axis, and I have the third axis, of course, let's say this is my z-axis. All right. Now, I have my rectangle AB cross CD. So that will be, my A and B. Here's my A, here's my B, and then let's say here's my C and D. And so I'm gonna have this rectangle on the XY plane. So here is the rectangle. Right, this is my rectangle R, capital R. Right. Now, guys, of course, so we have this function f, which is continuous on the rectangle AB cross CD. So which means that, you know, for each point of the rectangle R, the blue rectangle here, you're going to associate. So for each point, you're going to have the image of the point by the function f, right? So, you know, for example, let's say this point here goes somewhere here. You know, this one here goes somewhere here, right? Etc. So this one here goes somewhere here, and this one here, let's say, goes somewhere here, right? So you're gonna have some, actually, what I call a surface. All right. So this is the graph of your function f, right? This is f of xy. So this is your So it's just the image of the rectangle by the function f, right? So this is your f of xy. Right? So we have this region bounded. So we have this region bounded by, you know, between the graph, the graph of f of xy and the xy plane. So what I mean is this region here, you know, this one here. Right? So again, you're going to have like sort of a solid bounded by this the graph of the function f, right? And your rectangle R. Okay, and of course the idea would be, so that the goal now would be to find the volume of this solid S. So this is, here's my solid S. This is my solid S. This one here. And so we want to compute the volume. So the goal would be to find the volume of S. Okay. Again, S, that's the region bounded by the graph of f of xy, bounded by between f of xy and the, you know, the rectangle or rectangle R, right? The xy plane and the xy plane. Okay, so what I mean by the xy plane is just the rectangle R. the blue rectangle, right? Rectangle R. All right. So, well, the idea again is the same. We're gonna divide now we have, of course, two intervals, right? The interval AB and the interval CD. But we're gonna do the same thing. We're gonna divide the AB, both AB and CD, into n subintervals, right? So, so the steps. So first step would be to. So step one. So we're gonna divide AB into and subintervals. This of equal width again, subintervals of equal width. Delta x, and again we're gonna have the same formula for delta x. It's your length of your interval AB, which is b minus a, over we have n subintervals of equal width, so it's over n. The same for the interval CD. So we're going to divide this CD into n subintervals. So into n subintervals of equal width. Right? Delta y, of course, because so your variable y belongs to this interval CD, right? So delta y equal to, and now I have interval CD, so the delta y would be d minus c over n, right? Now, so if you do this, then you're gonna get like very small rectangles, right? So, you know, I have my x-axis, my y-axis, I have my AB interval, AB, I have my interval CD, and now I divided, so here's my rectangle R, right? That's AB cross CD. It's AB cross CD. Right, now I divide my my interval AB into n subintervals. So we're gonna have, as usual, so we're gonna have x0. So A is x0, this is x1, this is x2, etc. And B would be xn. Right. The length of each subinterval is delta x. So this is, you know, this is delta x. This is delta x again, etc. Now do the same for the interval CD. So C would be y0, and then we're gonna have you know, y1, y subscript 1, y subscript 2, etc. And then D, of course, would be y subscript n. All right. Now, of course, the length of each subinterval here and the interval CD is delta y. So this is here, this is delta y, this is delta y, etc. And now, so actually your, so we divided our rectangle into sub-rectangles, right? Like small rectangles here. Right. So each small rectangle here, the width, so here would be, this would be, so for like for this there is a small rectangle here, the base would be delta x, and the height will be delta y, right? This is here, this is delta x, and here this is delta y, right? And so we have this small this small rectangle here, this one here, etc. Right? So, so we're gonna have these small rectangles, and so let's call these smaller rectangles R subscript ij. So let R subscript ij equal to the interval, let's say x subscript I minus 1 xi times across the subinterval y j minus 1 yj. Okay. So let this R subscript ij be the ij rectangle, right? So be the ij rectangle. Right? So for example, this small rectangle here, this one here would be R, this would be R11, right? The next one here would be, let's say R21, this is, let's say this is R21, R31, etc. This rectangle here would be R12, you know, R13, etc. Right? So yeah, we have all these small rectangles. And what would be the area of this small rectangle? So the area of this of the rectangle Rij would be just delta x times delta y, right? The base times the height. So the area of this rectangle R subscript ij. So the area of R subscript ij, it's just well, let's call this area delta A. Okay. Again, this is a Greek letter, right? This is a capital delta, right? This is delta A equal, so that will be equal to delta x times delta y, right? That's the area of just small rectangles. So I'm gonna call this this delta A or delta x times delta y the area element. Okay, this is, I'm gonna call this delta x times delta y the area element. So now the volume of my solid S, so there is so for each rectangle R subscript ij, there is there's a region S subscript ij, which corresponds to the, you know, so to the rectangle Rij. So for example, you know, you have this again, we have these three coordinates here, x, y, and z. All right, so we have this rectangle R. Okay, and we said we divide this this rectangle I into small rectangles, right? So I have a small rectangle here, for example, a small rectangle here, etc. And then I have my function f, right? Here's my function f. So right, let's say this is my f of xy. You know, this is the graph of f of xy. So for each rectangle Rij corresponds a region under f of under the graph of the function f, right? So you know, you have this small rectangle here. So we're gonna have a small region here. All right. So let's call this region Sij, right? So let's say this is, here's your rectangle, small rectangle Rij, right? And so this region here would be Sij, right? So this is, let's say, this is Sij. Okay. So the volume of this region Sij would be, of course, you're going to have your the area of your rectangle, Rij, right? Times, now the height would be, let's say, f of, f of xi yj, right? So this is, so let this S subscript ij, right, be the corresponding region. I'm sorry, guys. I mean, my graph is not, it's not perfect, but and again, guys, if you have questions, just let me know, right? So this Sij is just the corresponding region under the graph of f of xy, right? So under f of xy. Okay. So now we can approximate the volume of Sij by, so it can approximate it by, the area of your rectangle here, Rij, okay, Rij times, and here, let's say the height is given by, some point here, let's say f of, f of xi yj, and so this is, let's say here's your f of xi yj. Okay. So the volume of Sij can be approximated by f of, let's say, xi yj times, of course, the area of your rectangle, which is delta A, right? Which is the same as, this is just the same as, so f of xi yj, and then delta A is just delta x times delta y, right? Now, the volume of the whole solid S would be, of course, the sum of the volume of all the, these regions Sij. So the volume of S, the whole solid, right? Let me just remind you. So the S would be, the region bounded between the function f and the xy plane, right? So the volume of S would be the sum of the volume of all these Sij. So volume of S is going to be equal the sum. So the summation here, so we have, of course, because we have two variables, right, guys? We have x and we have y, and we divided each interval, so the interval AB into n subintervals, and the same for the interval, CD, right? So we have two different variables here, xi and yj. So so the volume of S would be, so here summation is going to be over I, so I going from 1 to n, okay, and then j, because we divide our interval CD into n subintervals, right? y0, y1, y2, etc. So so here's volume of Sij, which is, as I said, we can be approximated by this sum 1 f of course, xi yj, delta a. Okay. So then, by definition, actually, so this volume of S, as n gets large, right? So the volume of S, so as n approaches infinity, volume of S would be equal to limit. Now, of course, we have I, I goes to infinity, right? And also J goes to infinity. Right, of course, the sum here says f of xi y, so yj, right, delta a. Okay. So this would be, of course, a double. Sorry, here I meant n, of course, here. So n goes to infinity, of course. Here. So here, n going to infinity. So this I, and so here over, oh, sorry. So n goes to infinity, and going to infinity. So here I going from 1 to n, and sorry, j going from 1 to n, right? And so that will be the double integral of f of xi, oh sorry, f of xy dA. Right? And so here we integrate over the rectangle AB cross CD, right? This is the rectangle over the rectangle AB cross CD. So this is kind of like a double Riemann sum, right? For a single variable, we have a Riemann sum. So this is kind of a double Riemann sum of the function f over rectangle. So this is double Riemann sum of f over, of course, the rectangle AB cross CD, right? So so that will be, so this this area element delta A or dA, as I said, we call this dA or this delta A. This is our area element, and it's just a dx dy, right? So that will be equal to f of xy dx dy, right? Of course, x goes from A to B, and y belongs to the interval CD. Right? Of course, here dx dy. The order here, guys, is important. Okay, the order is important, right? In some textbook or some literature, you can dx dy actually, and we're gonna see this later in chapter 8 actually. So this dx dy can be written as, so just a remark. So this dx dy can be written as actually dx, and there's this is called the wedge product. So dx wedge dy. So this is the wedge product. So this is called the wedge product. So we will see this in chapter 8 with differential forms. Anyway, so this is just a different notation for dx dy. You can find dx and this wedge product with dy. Anyway, so how do we evaluate double integrals? Well, so how do we evaluate double integrals? As I said, so you start with the so we have this CD and then AB f of xy dx dy. So you see, guys, this is, so first we start with integral with respect to x. So I mean, another way to write this, if you want to use parentheses, would be, so this is integral from c to d, and then you have like kind of like parentheses, and then we have integral from a to b f of xy dx, right? And here's my parentheses, and then dy. Okay. So first we have this integral with respect to x. So what we do is we integrate with respect to x, assuming y to be a constant. Okay, so first, so this is a function of y. So first, so we integrate with respect to x, assuming y to be constant. Assuming y to be constant. All right, and then of course, and then we integrate with respect to y. Right, so the step 2. We integrate with respect to y. All right, so let me just give you an example, and then I'm going to give you an exercise. So for example, an example here. So let's say you want to integrate let's say x squared times y. All right, dx dy, dx dy, again, that's my my area element, right? Dx dy. X is from, let's say, goes over the interval, let's say 1, 2, and then y goes from it belongs to the interval, let's say 0, 1. All right. So if you use, as I said, if you use parentheses, well, first, so we have to integrate with respect to x. You assume y is a constant, right? So here, so we integrate with respect to x, assuming y to be constant. Okay, so well, y is a constant, so we just integrate the x squared. Of course, integral of x squared would be just x cubed over 3. So we're gonna have the first, you keep the first the integral here 0, 1. Then we have integral of x squared. As I said, it's just x cubed over 3. The y is a constant, so I'm gonna just keep the constant y, and this is evaluated between from 1 to 2. Okay, and then there is this dy here, right? So if you want to keep the parentheses, so here's my parentheses, right? So first you just substitute x by 2, and then you substitute x by 1, right? So you would have, so this is integral from 0 to 1. This is my dy. So let's say this is my parentheses, and then you substitute x with 2. That will be 2 cubed over 3 y, right? Minus, and then you substitute x with 1. So it's 1 cubed over 3 y. All right. And so that will be equal to, so this is equal, integral from 0 to 1. Here's my dy. So it's 2 cubed, it's 8 over 3 y minus 1/3 y. All right, so and that's what I mean here by a function of y. So you get, as you can see, guys, you when you integrate with respect to x, assuming y is a constant, you get a function. You see here, this is now a function of y. Right? So yeah, anyway, so 8 over 3 times y minus 1/3 of y, that will be 7 over 3 y dy. Right? And now I can just integrate with respect to y, of course. And 7 over 3, it's a constant. Integral of y would be y squared over 2. So this is 7 over 3 y squared over 2. Y squared over 2. Evaluated between 0 and 1. So if y is 1, so it's 7 over 3. 1 squared over 2, half, minus 7 over 3 times 0 squared over 2. All right, so that will be equal to, of course, this is just 0. And that's here, this is 7 over 3 times 1/2. It's 7 over 6. All right. So again, this 7 over 6, this is supposed to represent probably the net volume of, you have this, so x-axis, this is y-axis, this is the z-axis. So x goes from 1 to 2, is 1 to 2, and y from, from 0 to 1. All right, and then you have your function f of xy. So in our example here, our our function f of xy is the x squared times y, right? That's my function f here. My function f. All right, and let's just suppose this is, let's say, so here's my first rectangle. My rectangle would be, interval 1, 2 times. So 1, 2 times 0, 1. So I'm going to have this rectangle here. All right. So this is supposed to be my rectangle R. My rectangle R, which is 1, 2 cross 0, 1. Right. And then, of course, you have, so the image of this rectangle by the function f would be some, some surface here. Okay, this is my function f. That's the image. This is f of xy. That's the image of my rectangle R by the function f, right? And then, of course, we have this solid, this region bounded between, between your rectangle and the graph of f of xy, right? So, so here's my, let's say, right? I have some solid here, right? And this would be the volume. So this is my solid S, or my region S, right? And so this 7 over 6 is supposed to represent the net volume of this solid S, right? Anyway, So here's an exercise, guys. Well, first, is there any question, guys? I'm not sure if you did double integrals in Calc 3. I mean, it depends, of course, on professors. Because I mean, double integrals is like the end of the the material. So sometimes it's covered by the professor, sometimes it's not. But anyway, I mean, if you have seen this before, that's good. If not, please feel free to ask questions, right? So here's an exercise. So just to evaluate a couple of double integrals over rectangle. So please try to integrate so first integral, let's say it's so integral of let's say x y squared minus y, so dx dy, so x belongs to the interval, let's say 0, 1, and y belongs to the interval, let's say 2, 3, right? 2, so the first integral, second integral, let's say it's x over y plus y over x, right? Dx dy, x, let's say from 0 to 1, and y is, let's say, from 2 to 4. All right. Oh, sorry, x, let's say it's from 1 to 2 because it's, let's say here it's from 1 to 2. We're gonna have log, so it's not in the domain here. So here, x from 1 to 2. All right. Okay, guys, let's say you have 5 minutes to think about this exercise. And of course, please let me know if you have any question, right? So after this exercise, I guess I'm gonna discuss when can we switch the order of integration, right? Because as I said, the order of integration is actually important. So here we're supposed to first integrate with respect to x, and then we integrate with respect to y, right? But yeah, after the exercise, we will see when can we switch the order of integration. And then after that, I guess we can discuss the double integrals over general regions, right? Because here, we integrate over rectangles, right? Next, we'll see how to integrate over general regions. So again, guys, this is, this double integral is supposed to be sort of a review. But please let me know if I'm going too fast because, again, it's supposed to be a review. So, but anyway, if I'm going very fast, so just let me know so I can slow down a little bit, right? And as I said, this course, it's all about integrals, different kind of integrals, integrals over paths, integral over surfaces. We're gonna see different theorems about integrals of vector fields, Gauss theorem, Stokes theorem, Green theorem. So it's all about integrals in this course, right? So that's why I had to start with this single double integrals, right? It's supposed to be a review, but I guess that's a good starting point. So does anyone have the answer for number one, for the first integral?
I have 5/2.
5/2?
Yeah.
Okay. And what about -3, Dylon? Okay. Okay, so we have two different answers. All right. Well, actually, we have like 4 minutes. So I'm going to do, guys, I'm going to go over number one. And then I will probably come back to number two next time because I see there are different answers for number one. So let's see how it works. So you're done with the Dialon? You're done with number two too? Oh, that's for number two. All right. So your answer, -3, is for number two. All right. Oh, okay. Okay, I see. anyway, so as I said, we have just 4 minutes, guys. So let me go over number 1, and then I will come back to number 2 next time. And again, next time I will continue with the double integrals over general regions. We'll see when we can switch the order of integration, and then of course I will talk about the triple integrals, right? So for number 1, this is from 2 to 3, from 0 to 1. So x y squared minus y. So we have this dx, dy. So as I said, so first we start with integration with respect to x. So we integrate with respect to x. Here, with respect to x. And of course, assuming y to be constant. Assuming y to be constant. So, so that would be equal to, so first we keep this the integral from 2 to 3 and the dy, right? Now, I have to integrate this x y squared. Y squared is just a constant. I mean, y is a constant. Obviously, y squared is also constant. So just we integrate x. Integral of x is just x squared. Sorry. It's x squared over 2 times y squared times the constant minus, and then y is a constant. And if you integrate a constant with respect to x, it would be x times the constant. So that says minus x times y. And we have to evaluate this from 0 to 1. Okay, so so then we substitute x by 1 and then by 0. This is the integral from 2 to 3. So it's 1 squared over 2, y squared minus substitute x by 1. So it's 1 times y. All right. And now we substitute x by 0. So it's just 0 squared over 2, y squared minus 0 times y. All right. And then we have our dy, of course. So, all right, so then this is, this whole thing here is gonna be, sorry. So this whole thing here is gonna be just 0, right? And then we have integral from 2 to 3. So we have half of y squared over 2 minus y, and then have dy. Now, so we get a function of y, you can integrate with respect to y. Integral of y squared, that will be y cubed over 3. So that's y cubed over 3. And there's a 2 constant in the denominator. So I'm going to just multiply by the 2 here in the denominator. Minus, and then integral of y, which is y squared over 2. And dy. All right, so then just substitute now y. Sorry. So here we have to evaluate, right? From 2 to 3. All right, so this is 3 cubed over 2 times 3 minus 3 squared over 2. And then substitute y by 2. So it's 2 cubed over 2 times 3 minus 2 squared over 2. So that'll be equal to, so 3 cubed over 3, that's 27 over 3, that's 9 over 2. So this is 9 over 2 minus 9 over 2. All right, minus, and then we have 2 cubed over 6. So that's 4 over 3 minus 4 over 2. Right, so that will be equal to, so this is 9/2 minus 9 over 2. So that's just 0. This is just, here's 0. And then, so that's minus, so 4 over 3 minus 4 over 2, multiplied by a common denominator, of course. So this is minus, so it's 8 over 6 minus 12 over 6. right? So that will be equal to minus negative 4/6, which is of course positive 2/3, right? So that's what you got, David, right? You said 2/3, right? Okay. All right. So any question about this number one, guys? Okay, I guess not. All right. Okay, so I'm gonna, I guess, sorry, I went over time. So I'm gonna stop here, guys, for today. And I will see you, I guess, on Thursday, right? 10 a.m. Okay. Thank you, guys. Thank you, everyone.
Excuse me.
I will see. Yes.
And we don't have homework for Thursday, right?
Not this week. Probably next week I will assign the first homework.
Okay.
Yes. Sure.
Thank you.
Thank you,
Bye.
everyone. Thank you, guys. I will see you on Thursday. Take care. Thank you, Mariki.